So the goal for the talks is really just going to be to get you familiar with some computational algebraic software. I'm going to use primarily Magma. There's also Sage out there, which hopefully if I have time, I'll talk a little bit about Sage. The last time I taught this, I used only Sage and thought I'd challenge myself to do this all in Magma. So we'll see how this goes. But if you have any questions at any point, please just shout out and ask. I'm going to try and cover some stuff, but Magma is an amazing software. It really does a lot. So I'm barely going to be able to show you, a fraction of what it does. And if at any point I skip over something that you think would be worth seeing or something doesn't make sense, just interrupt me. I'm happy to answer questions when possible. I should also warn you, I have none. I have no formal training in computer science. So if you're a computer scientist, please bear with me. So one of the nice things about Magma is that they have an online calculator available. And so if you just go to Google or Bing or whatever it is you search the internet with and type in Magma calculator, the first thing that comes up is the Magma calculator. And I'll zoom in if possible. Well, maybe it's actually already zoomed in enough. Can people see what's going on the screen? There's a place to enter your code, and you can do things like 1 + 1, and you bigger. Let's see. I'll have to scroll down when I evaluate. Is that better? Yeah? Little smaller? All right, we'll stay here. You can do things like 1 + 1, hit submit, and look at that, it's 2. Great, right? So if you want to do multiple lines, the one thing that you should first realize is that every line needs to end with a semicolon. If you don't do that, if you do now like 2 + 1, it'll throw an error when you hit submit. And this is probably the most common error. If you see a bad syntax error, it probably means you lost a semicolon. And now the last line doesn't need a semicolon, but it's probably worth just always writing it because you'll forget if you're, anything like me. So the next thing that you might want to do is maybe you have a conjecture for what 1 + 1 ought to be, and you want to have it return either true or false whether or not your conjecture is correct. So to do that, you do =2. That's my conjecture. So you do EQ, and that'll return a logical operator true. So 1 + 1 = 2. This is really useful when you're writing code because you want to do if something's true, then do something else, or for all things that this is true. So this is worth knowing how to do. So the other sort of basic objects that you want to have floating around are integers, real numbers, rational numbers, and the complex numbers. So the ring of integers is just integers with parentheses at the end of it, and I'll tell you why there are parentheses later on, and that just gives you the integer ring. Then there's integers. This is a weird keyboard for me, and I'll admit I'm a little nervous, so I might type a little poorly today. Rationals. There's the real field.
Is this just somehow announcing their presence?
Yeah, well, it's just defining them. So we'll give them names later so we don't have to keep typing real field and rationals. But I want to show you something. Complex field. And we'll hit submit, and it'll just tell me what all of these objects are. And you can see there's the integer ring, there's the rational field. And then the real and the complex field comes with precisions, right? Because these are, real numbers are infinite decimals. We're not going to compute all the decimal expansions of these. We stop at some point. There's some floating point calculations. And the initial precision is 30 bits. You can change the precision by throwing in, say, 100 or 20. And now we'll have our real field out to 100 bits of precision and our complex field out to 20 bits of precision. This is worth knowing because we are limited in our calculation sizes that we can do in terms of our memory and the amount of computational time we can run because we're using this free online calculator. 120 seconds doesn't seem like a lot, but you'd be surprised how much Magma can compute in 120 seconds. If you bump up against that limitation, you can go online and download it. One of the downsides to Magma is it's not free and open source, but the Simons Foundation has a grant with all U.S. institutions, so many of your institutions have a Magma license already, and it's just about coordinating with them to download it. If you have questions about that, I'd be happy to talk to you about it, but my guess is you're all computer savvy enough to follow the documentation and to download Magma and all the information that you would need. It's also maybe worth pointing out the handbook will also be your best friend, so maybe I'll just open that up now, where you can search all sorts of different stuff for how to do things. All right, so back to these. So some other things you might want, we've heard about finite fields, so you might want to look at the field of size 5. So to get a field of size 5, you do GF5. I'm sorry, Keith, I didn't write the code. Submit. And now we have a finite field of size 5. You can do the finite field of size 25. And now one thing to notice is, again, the finite field of size 25 is not Z mod 25Z. Right? These are different things. Z mod 25Z has 0 divisors, so this isn't a field. Yeah?
Just so Keith is happier, you can type finite field 5.
Oh, you can? That's so many more keystrokes, though.
You already typed complex fields 20.
But and you know, is CC 20? Oh no. So I guess what I would do now is maybe before we go any further, let's call the integers ZZ, the rationals QQ, because you might want to use Z or Q for something later on, RR and CC. And the thing that I want to point out about GF25 is that this isn't Z mod 25Z, right? This is a degree 2 extension of GF5. And so somehow you might want to get your hands on what that other element is that's not 1, 2, 3, 4, or 5. And so what you might do is say, let's call this field F, and maybe alpha, alpha will be that element, and I'll define F to be GF25, and that new element I'll call alpha. And so, we can do, say, let's hit submit. Now nothing's going to get returned here, except for GF5, because I didn't give that a name. Now everything has names, and that's all I've done. I haven't called anything. But you can do something like minimal polynomial of alpha, and it'll tell me what the minimal polynomial of alpha is. We'll hit submit, and there it is. Now it's giving me my variable is $.1. This is incredibly frustrating because I didn't give it a name. And so you have to give it a name if you want to look at things that are nicer than this. And so let's drop this down to the next line. Let's call this polynomial f, and the variable will be x. Oh, and maybe I should also say you need : equal sign to define an object to be equal to whatever it is. And no, it doesn't. I try and put spaces when I remember, just so that it's a little more readable, but I'll forget. And now our minimal polynomial of alpha is x squared plus 4x plus 2. A little bit easier to read. You might also want to work with the integers mod 25, right? You might not only be interested in the field with 25 elements. If you want the integers mod 25, integers 25, maybe we'll call this I. And you know what? Maybe I'll teach you now how to comment something out. // will comment things out. So I won't keep returning all the stuff above it. I don't need this minimal polynomial for anything later. And now I is our residue class field ring of integers modulo 25. What's nice about this too is what's hidden here is that this ring comes with a map. It comes with a map from the integers down to the integers mod 25, which is reduction mod 25. And you can actually get your hands on that map by just giving this a second thing that you're defining. Let's call it map for now. And map, so that's all defined. But let's say we have an integer we want to reduce mod 25, map 1, 2, 3, should return 123 mod 25, which is, of course, just going to be 23. The other way you could do this is you could coerce the element 1, 2, 3 into the ring of integers modulo 25. And the way you do that is you take your field you want it to be coerced into, the ring you want it to be coerced into, put an exclamation mark and then the element that you want to coerce. Oh, I don't have the number lock on. That's why. There we go. And now I should get that these are both 23. And in fact, these should be the same.
But if you just wrote 23 equals, it would say false, because it...
I think so, yes. Because one would be an integer. But let's see. Whoops. Oh, no, it's still true. Interesting. Well, let's see. What is the type? How does Magma think about, this object? What type of object is it? It is a different object, right? Because type 23... Come on, Amherst. Sorry, I'm really having trouble with this keyboard. I'll get better, I think. See, they are different elements. So there must be a way that Magma knows how to compare these things intuitively. Or innately, built in. So the other thing that you might want to do is if you don't have just a polynomial that you want, but you want a ring of polynomials, you want to look at the polynomial ring, say, with rational coefficients. Let's clean some of this mess up. There's stuff floating around here. Let's let P be the polynomial ring over the rationals. And let's, with variable x. So x is going to be my variable. That's the second thing that's given on the left-hand side. And let's let f be, I think I wanted to start with x squared plus 5. Okay, and then we'll return f, and of course that's just going to give me back my polynomial. So there are lots of things you might want to do with a polynomial. For example, you might want to know, is this irreducible? So you'd say, is irreducible. Did I mistype that? Irreducible. Yep, it is irreducible. No one's surprised though, right? Great. And similarly, you could also ask for its roots. It will give you its roots over the base field that it's defined. So here we should expect that we get back just an empty list. And in fact, that's what we get. I'll show you what the roots look like when we actually have some floating around. So we have an irreducible polynomial. Oh, well, I guess the last thing you might be interested in doing is evaluating it at some point. So evaluate f at, I don't know, lousy with 5. So let's use a 2. Submit. And 9, 2 squared is 4. Yeah, that checks out. So that's how you would evaluate a polynomial at some point. And of course, you don't need to define the polynomial this way to do a lot of this stuff. You can have it floating around with the $.1s if you don't want to deal with defining the polynomial ring if you have this popping up from some other way, the polynomial. But it's nice to read what you're doing, to have these things in terms of x. Okay, so we have an irreducible polynomial, degree 2. Maybe we want to define a number field based on this. So let's define the number field k. I'll make its primitive element a, and we'll just do number field. Oh, and when in doubt with Magma, one of the things that I do like about it is the commands are generally intuitive, and they're almost all just camel-cased what you would expect them to be. If you want the number field associated to a polynomial, just type number field, camel case. Do you know what I mean when I say camel case?
No.
Capitalize the first letter of each word. Right? Because it's got humps. Well, all right. Camel case is alliterative, though, so it's easier to remember. And now we have our number field with defining polynomial x squared plus 5. And now we can start doing things with this number field. It's worth pointing out at this point maybe that this type function is useful not just to recognize what sort of types of things you're getting out, right? This is going to tell me it's a number field number. You can also do, I hope, question mark, submit, and there are no references for this, although I guess if I did, well, I'll maybe come back to this in a second. So let's get rid of this. So now the first thing that I want to do is look at maybe the roots of f over this new field. So let's change the base ring of our polynomial f to be k and see how the roots change. So I'm going to let fk be, let's make sure I get this right. It should be change ring of f to k. And now, thank you. I would have caught that. Change ring, FK, submit, error. Up. Oh, here we go. Thank you. And no J probably, right? FK. And there we go. Notice it's back to $.ones because I didn't define what the variable should be in this new polynomial ring. It's not the polynomial ring over the rationals anymore, but who cares? $.1 is as nice a variable as any other one. That's not completely true. But now we can compute the roots of F capital K, and it should return that the roots are minus A and A, right? Plus or minus the square root of 5. Minus 5, excuse me. And you can see it's giving me back a sequence whose entries are vectors, and the vectors are the root and then the degree, the multiplicity of that root of the polynomial. And so if you wanted to get your hands on, say, the first root, well, you want to get the first entry here. This will give me back minus A comma 1. And maybe I'll have it stop returning this. And there is the first root of this polynomial. And then you can start doing algebraic manipulations to this. Maybe we want to square this and see what happens. Again, no one's going to be so surprised by the result. If you square A, you get back minus 5. Great. So the next thing you might want to do with this number field is compute its maximal order, the ring of integers. So O will define to be the maximal order of K, and O will come back as the maximal order. We can get a basis for O, and this is where things get a little sad. It just returns the basis is the first generator and the second generator. This is not the most useful thing. Yeah, Eric?
Can you convert between indexing from 1 and 0?
No, I think it's pretty much set in its ways. As Magma likes to put it, they've made their decisions that they start with the first element as 1, which I think is maybe more natural to mathematicians than starting with 0, which is why they made that choice. I never loved that the first element in Python of a string is the 0th element. Does that seem weird to anyone else? That's just me? No, not just me? Okay, good. I don't know. When I start counting, I start with 1. So if you want to figure out what the heck these things actually are, you can get your hands on the first element in the basis and ask what the minimal polynomial. I can't type today. I'll say today, but it's probably a larger issue. Submit. X minus 1, so O.1 is 1. Now, I just want to point something out while we're here. If you hit the submit button, watch what happens to the clear button. It becomes cancel for a second. So if you're running a long computation and you want to cancel it, you can click the cancel button, it'll stop it. I don't have anything long going right now. Just be really careful about doing this because after you hit cancel, it becomes clear. And if you don't move your mouse off of the clear button, you might accidentally click it, which can be trouble, right? You lose everything that you've typed in. This isn't saved anywhere. It's also nice to have like a blank text document. Maybe you're on a Mac and you want to use text edit. Have that open and be copying and pasting things into or from it so that you don't, at 3 in the morning, accidentally hit cancel twice and clear out everything that you had been doing and throw your computer out the window. I've never done that. Submit. The second element is exactly just A, right? Our original square root of minus 5. Okay, so what else would we want to do? Well, you might want to know what the discriminant of the number field is. So let's calculate the discriminant of O and hit submit. And Alvaro, I know what you're thinking. I'll mention it. So the discriminant is minus 20. Now I want to point this out. You can ask for the discriminant of K. The discriminant of K does work. Whoops. You have to click the submit button though. And look, I got back the same thing. It's not true in general that you'll get back the same thing from Magma. Magma has made their decisions, and they've decided that the discriminant of a number field is the discriminant of the polynomial that you decided to use to generate it. So if I come up here and change my polynomial to be, instead of x squared plus 5, I make it 125, let's say. This will define the same field because I've changed this by a square, but now the discriminant's different. So when you're, yes, but they've made their decisions and that's what they do. So just be aware of this. There are some funny things with any software. This is the first one that has really caused problems for me with Magma, sort of at the most basic level. But if I go back and I do discriminant, you know what, of O with this new polynomial, I will get back minus 20. It really does give me what you would expect the discriminant to be, which is the determinant of blah, 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 what you've already learned about. Make sense? Everybody feeling all right? All right, so the next thing you might want, well, maybe we want the Galois group. Okay, it's quadratic, so it's not going to be super interesting, but I should at least show you Galois group. Galois group of K, submit, and it's the symmetric group acting on two elements of order 2, and you can do lots of fun things with this. You can also do the Galois group of a polynomial. Of course, the generating polynomial should give you back the exact same thing. So there's the Galois group, but there's another group that we've heard about today that might be interesting, and that's the class group. The class group, I think I need to do actually, let's see. Class group submit. Excellent. So it's an abelian group. It's isomorphic to Z mod 2Z. They dropped the second Z, but that's okay. Okay, so it's class number 2. And it's obviously going to be cyclic. There's only up to isomorphism 1 group of order 2. But you might wonder, well, what are the generators of this group? So let's give it a name. Let's call it G, because I'm not very creative. G. And you can get your hands on the generators. Whoops. Generators of G. Oh, great. It's the generator of G, G dot 1. And of course, you can get your hands on it too by just saying, well, the actual element itself is going to be G dot 1. If you do like a group dot a number, it will give you the first, second, that number generator. So G dot 1 is G dot 1. Great. Not very useful. But in fact, you can get your hands on what the element itself is, because hiding around here again, there's actually a map that goes from the abelian group back to the class group. So it takes elements in the abelian group and actually returns the concrete or a representative in the class group. So we can do map G dot 1 is still going to give me back just G dot 1. But if I plug in map now and plug G dot 1 into map, it will actually return a generator. So this is the ideal generated by two elements. I remember I have a basis of O, 1 in the square root of minus 5. And so it gives me sort of the coordinate vectors of each of the elements with respect to that basis. So the first element is 2, the other element is 1 plus the square root of minus 5. And there's my ideal and my generator. I can define ideals up here by doing lowercase ideal, which is a little frustrating, in O. Is it a vertical pipe? Yes, it is, of course. Maybe we want the ideal generated by 6. Let's see what happens here. I just get back the principal ideal of O. You could map this back to your abelian group to see, is this trivial or not? Of course, it's going to be trivial because it's a principal ideal in the class group. So notice I don't want to plug this into map, right? If I plug this into map, I should get an error because the map goes from the abelian group to the set of ideals. So now I want to go from the set of ideals back to the abelian group to see if it's trivial or not. And so I want to do the inverse of map and then evaluate that at this ideal, which should give me back the identity element, which in this case is 0. So I get that back. That's great. The other thing you could do is you could factor this ideal. So you'll type not factor, but factorization. Submit. And now we have our factorization of this ideal. It factors into 3 ideals, right? That generator, right? This first ideal generates it, but it's squared now. And then so 2, we can see ramifies, and 3 splits completely. These are the 2 ideals above 3. Everybody okay? Making some sense? Question?
So when you have a group that's like isomorphic to something else and you define the group comma map, is there a way to look at the map and understand what it does?
Yeah, there are lots of things that we can do with the map. Let's.
Could you repeat the question here with the microphone?
Oh yeah. So the question was, when you have a map, like I've defined map here, you have G comma map. Can you get your hands on map? So my guess is a lot of it's going to be hidden. It's not going to like give me a polynomial back or something, but you could probably, let's see. Let's just see what it says when I just type map. And you know what, I'm going to comment some of the, maybe I'll teach you a new trick. You can batch comment things out by doing /* at the beginning and */ at the end of what you want commented out. And now instead of doing a bunch of slashes next to everything. So if I just ask map, this just tells me it's the map from the abelian group to the set of ideals. So not a lot of information there, but maybe we can do the kernel. Fingers crossed. Nope, you can't. So I'm not exactly sure all the stuff that's available, but let's see what happens if I do, let's see what type of object this is, type. So Magma thinks of this as a map. Great. Wasn't expecting that. And so now maybe what we should try is our question mark trick again. Question mark map. Oops. Map. Submit. And now there's a whole bunch of stuff that we can do. So if I want to see, say, function procedural mapping, I would do question mark map. I think I want question mark 1. Let me double check. I don't have it written down, but I think I want question mark map, question mark 1. Submit. Oh, farts. Let's see that. So I'm not sure now why it won't let me extract the actual information out of it. See, there's a ton of stuff. So maybe, there we go. So now here's where it's going to give me all the stuff that you can do with maps, representatives, blah, 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 blah. But this is such a generic map, right? There are minimal examples that it might not be so fruitful to scroll through this right now. So I'll look at more stuff that you can do. I'm surprised it won't give you something like the kernel. Other questions? Let's not delete that. Everybody okay? Ideals. Oh, I totally skipped over. So, of course, this is number theory, so we're interested in working with prime numbers, right? So you might want to be able to generate lists of prime numbers pretty easily. So let's maybe come back here. Let's comment out all this stuff, because I'll want it later. /*. Push it down to the bottom. And let's do primes up to 100. So this will give me all the primes less than or equal to 100. It is the closed interval, so if I did 97 here, let's change this to 97 and see that we still get 97 in there. Submit. Gives me primes up to and including the n that you put in there. You can also do primes in interval. Primes in interval 11 to 100 should, let's do 11 to 101. This will give me back, again, a sequence of numbers, all primes, smallest to biggest of the primes in there. And then another thing you might be interested in is a random prime. So random prime, let's say 100 here. So you would think that this would give you a random prime less than or equal to 100, but it doesn't. That's certainly not less than or equal to 100. It gives you a random prime strictly less than 2 to 100. So it's the number of bits that you want to work with. Keith, question?
No, I was
just stretching? All right. Just trying to be attentive. And so maybe we should make some lists of prime numbers. Let's see. So let's get some special primes. Maybe we'll start with something we know will be finite. The Vierich primes, Alvaro, is that right? What? Well, I have this example already worked out. So let's look at the primes P. So I want P in the primes up to, I think 3600 should work. 600. And so far I haven't done anything, but now I'm going to give it a vertical pipe and give it a condition that I want it to satisfy in order to be included in this set. So you can see I'm saying I want P, where P is coming from this set, or this vector, or sequence, I guess it is. And I want it to satisfy that if I reduce mod P squared, integers P squared, 2 to the P minus 1, I get back 1. And let's see what this set is. WP, submit. Oh, and now I have primes up to, I lost an S. Thank you. So embarrassing. Now let's hit submit and see if that does it. There we go. And these are the only two known Virich primes. Maybe you want twin primes. It's more interesting. Is it? I don't know. Probably. Maybe not. Keith's saying no, so I'll go with no. But still, maybe you want the twin primes, so we want primes up to, maybe I'll lower my bound. Let's change this to TP. Whoops. For twin primes. And maybe I'll make this a little more adjustable. Let's go up to n, and we'll set n outside. Let's say n is 100 for now. That's not very interesting. Let's do 1,000. And now instead of having it be 1 mod blah 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 piece, let's just say is prime p plus 2. And I need to change this back, or this to TP. It's up to blah blah blah. And now submit. Here are my twin primes. And so P and P plus 2 are both prime. You can get the number of these by just giving it, whoops, not there. This is what happens when you try and shoot from the hip. TP, submit. There are 35 of them in this range. And so you might start to wonder, oh, well, I wonder what percentage of primes are twin primes in this range. And then you would maybe divide by the number of primes in primes up to bound n. Copy and paste. And, man, this is going to return submit 524. So that's a little annoying, right? We usually think of percentages in decimals or numbers between 0 and 100. So maybe you want to coerce this into your real field so that it actually gives you a percentage. And okay, about 20%. Well, I wonder what happens as I increase n. Maybe we want to see how this evolves and compute this for a bunch of values of n. So rather than just going back and changing n each time and hitting submit, let's define a function that returns this ratio. The number of twin primes divided by the number of total primes in the bound that we looked at. So let's define a function. Here we go. So I want to get rid of n. We'll define a function. Maybe we'll call it percent t. It's going to be a function of the variable n. I need to do end function with a semicolon. And now I'll have it return this number. So let's scroll down this. I'm just going to hit submit, and it should not give me an error. Great. And now let's write a little code that computes this for some various values of n. So this is, of course, not the most efficient way to do this, but it's a great way to start seeing some for loops and defining functions and this kind of stuff. So let's say for, we'll do capital N in, I don't know, let's do it for 100, 1,000. You know what? Let's do 1, 2, 5, and 10. And let's do, not function, but percent t 100 times n, and end our for loop. Hit submit. Bad syntax. Oh, what did I? Yep. I need to do. I need to tell it what to do. Now let's see. Hopefully that works. And here we go. Okay, now you can start to see why you might not want the full precision here. This is a little bit hard to read. So let's change the precision from 100, which is way too much, maybe down to 10. hit submit, and now it looks like 32%, 32%, 25, 20. And what's nice about Magma is at the bottom here, it tells me how long it took to do the computation. It took 19/100ths of a second to do that. So maybe we can push this a little bit harder and change our values of n. See what happens if I put a 100 in there. Submit, and now you can really clearly see the clear button. Oh, excuse me, the cancel button, although that still didn't take that long. Now we're down to 16%. Maybe we'll try, comma 500. Steadily dropping, and so you could start to make some conjectures about how often primes ought to be twin primes. And as your range goes out, I mean, this isn't very convincing, but you might think that this is starting to look like it's going to go to 0, but who's to say it's not going to go to a 9th or something like that. But let's see how long that took. Less time. How could that be? Well, that's interesting. Let's try. Let's change this to that and submit. I really want to bump into the. No. I mean, it's still. Now we're at the 0.2 of a second. So maybe this is fairly impressive, right? Let's see what happens if we do 10 to the 5th. This should break pretty quickly.
Not only is it impressive, the competition is going to Australia, being done in Australia.
Coming back. But I think the time that we're seeing is actual computational time. It's not accounting for the transatlantic flight or whatever it is to Australia. But I mean, you can really start to get a lot of information about these statistics just from doing some simple computations and starting to see, oh yeah, it really looks like these things are decreasing and probably ought to go to 0 as n goes to infinity. So maybe let's go back to our number fields now that we've explored our primes. Maybe I'll just, again, batch comment this out in case we decide we want it again. And we're back to our number field. Maybe I'll get back to our good polynomial too. There we go. And so there's another group you might be interested in. Oh, and you know what? Let's change this to -2. So now we have a real number field, just the square root of 2. Submit. We've got our minimal polynomial, so our basis really is just 1 in the square root of 2 this time. The discriminant of both of these is going to be 8. You could see this is maybe the right polynomial to use to define this because these are the same. And let's look at the unit group. So G will be the unit group of O, our maximal order. Submit. Oh, I have to have it return G, of course. And so our unit group is an abelian group. It's isomorphic to Z mod 2. Z, of course, because we have plus or minus 1. Those are our roots of unity in here. And then we also have a copy of Z because there's an element of infinite order here. So that's a pretty interesting thing. You might want to get your hands on it. If you do G.1, it'll give you back one of the generators, and I forget if it gives you the interesting one or not. So, of course, we just get G.1, and let's see what G.1 squared is. Oh, it's probably additive, of course. 2 times that gives me back the identity element, right? Because that one's just 1, where if I do G.2, that'll give me back the second element, and oh yeah, now it's just 2 times G2. Again, not interesting, not a lot of information here, except that, well, I know G.2 is the element of infinite order, but doesn't tell me what the heck it is. Sorry, I get excited about these things. But once again, there's a map that will return, given an element in your sort of generic abelian group, this is the coordinate vector relative to the basis that we have. So this is 1 minus the square root of 2. Makes sense? And so you can do 2 times that and figure out what that's going to be and so forth. And in fact, I don't know. Let's just see. I should be able to square here. It might be angry. Oh yeah, that works as well. And so maybe you want to check, do these things actually equal the same? If I do squaring on the outside and 2 times g dot 2 on the inside and hit submit, are these things equal? And yeah, that's true. Great. Wonderful. This really is a homomorphism. Okay. Another thing you might want to know is if things are units and what their norms are. So let's see, what's the norm of A? A is our square root of 2. It's got norm minus 2. Is it a unit? Well, we already know the answer to that because we know the norm, but is unit, right? Is unit, that should say false. Oh, what? I wonder if, let's see, because it's a unit. Right now it's in the field, right? So of course it's going to be a unit. Everything that's not 0 is a unit in the field. So if we coerce this into the ring of integers, now it's thinking about it in the ring of integers where everything isn't a unit. This is why when you do unit group, you don't do the unit group of k, right? You do the unit group of O because the unit group of k is k throwaway 0. It's a field. Sorry. It's making some sense? Everybody okay? Questions?
What is A again?
A is our root of the polynomial that we gave it. I know I jumped around and it would be nice if I could fit this all on the screen. But A here is what I'm defining to be my single root of my polynomial f. Now I don't know if it's the square root of 2 or minus the square root of 2, but algebraically who cares, right? This is a choice of embedding. And so we're just going to work without making that choice. There will be times where you'll need to make that choice, and you'll want something like the real embeddings. I think I want K. I might want O. Submit. Oh, yep. Thank you. Embeddings. Maybe it wants O. Nope. Maybe real embedding. Well, I'm not sure. I shouldn't have brought this up. But I'll have it next time for you exactly what to do. I don't want to... Well, let's see. You type in front of 85 people you don't know. Real and complex embeddings. And it says, see this other chapter, where you might be going down a rabbit hole we don't want to go down. But lots of times in Magma, you'll get to this point, and I think the easiest thing to do is to expand all and then see if you can search through. But you can see the documentation isn't so bad. There's lots of things that you can do. And if you click on any one of these, it will tell you, it'll take you to like a minimal example where they use this, what it spits out, a little explanation. They really have commented the code reasonably nicely. But let's see if we can find the embeddings. Real precision. Let's see. F real. Be just embeddings. Oh, embedding maps. Blah, 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 blah. Well, let's not do this. How's that sound? I'll find it and I'll have a good example for you next time. All right. So I have 5 more minutes. I had another example about number fields. Let's just quickly, let's look at everyone's favorite number field, Q adjoin I. And, well, now I'm getting a mistake here because the unit group doesn't have an element of infinite order anymore. It only has the 4th roots of unity. The group G now should be isomorphic to Z mod 4Z, because I have the 4th roots of unity, but no element of infinite order. And it is right that A should be a unit, right? Because in this case, A is actually the square, well, plus or minus the square root of -1, and that will be a unit in the unit group, right? Or in the ring of integers, I should say. Agreed? So this should be true at this point. And let's look at how some primes factor when they're lifted up to this new number field, in the ring of integers of this number field. So let's say let's look at the factorization of the ideal in O of P for P in primes up to, let's just do 100 because that's probably going to be plenty. Whoops. So this will return a list of these and let's just say, let's call it list. I don't remember if I want to do anything or if I'll have time to do anything with this. Oh, and I need to have it return list, capital L. And so now you can start to see two factors as a single prime squared. Because I have to factor the ideals because in every number field you don't have unique factorization. So Magma just wants everything to be ideals. But if you are in a PID, you have unique factorization, you can recover it from the information from the ideals. So two splits, two ramifies, it becomes a square. 3 is inert, 5 splits into 2 different primes, and so forth. And so you might wonder what primes split completely. And we should have a conjecture about this, I think, from Liang's, or maybe not even a conjecture, I think he may have proven it. What primes should split completely, should factor, should be the ones that are 1 mod 4. And let's see if that's actually true. So let's look at the primes P. Let's not look at their factorization anymore. Instead, so let's look at the primes P such that the number of factors in their factorization equals 2. 5, 13, 17, 29. Are these all 1 mod 4? Yeah, and so let's just compare this to the list of, well, let's just copy and paste, and maybe I'll call it list 1. Oops, not alt. I'm used to using a Mac. And paste, we'll call this list 1. And now instead of looking at the factorization, let's reduce it to integers 4. So I want to reduce it mod 4 and make sure it equals 1. And now let's do list equals list 1. And I don't want to return that anymore. We should just get a true back. And we get back a true. And so now maybe we want to do up to 100 isn't really the most convincing, is it? No, maybe you want to do this out to 1,000. And submit. And that's true. Maybe we can do 10 to the 5th. True again. So now I'm starting to convince myself that this conjecture is true, and maybe we'll see a proof of it at some point. So I think I'll stop there for today. So if there are questions, I'm happy to take them. Or if you are things that you want to see, feel free to email me. My email is hdaniels@amherst.edu. I should also, my first name is Harris. It's not my last name. This tends to be a point of confusion. So if you see me, you can just call me Harris. But hdaniels@amherst.edu. I'm happy to take suggestions of other things to cover. I'll start with elliptic curves next time. Thank you.